It's probably actually excessive precision. It's probably too precise for the process. The reason that we're able to achieve incredible performance using a silicon plate is
Silicon has changed the world in many ways, in semiconductors for electronics, in photovoltaic cells, or even in glass that we use daily. Today, we'll be talking to a person from a company that manufactures bipolar plates made of silicon. So something we haven't seen before. Welcome to Hyfindr Tech Talks. Today I'll be joined by Daniel Zafir. Hi Daniel, welcome. You're a neuroscientist, but you're now deep into the hydrogen economy, as I understand.
That's right.
And working at SILTRAX, building global partnerships, right? Yeah.
That's right, Stephen. Great to be here. Thank you.
Thank you for coming all the way. So Daniel, bipolar plates is what you guys make. Yeah. So let's just go straight in. What does a bipolar plate do, and where can it be found?
Definitely. So the bipolar plate is one of the most central elements of a fuel cell or electrolyzer stack.
Yeah.
I guess it provides the structure to the stack, as you can see here. We've got one.
Yes.
Each of these cells is a reaction chamber where hydrogen will react with air to create energy and water as a byproduct.
So these ones are the cells, and they are always made up of bipolar plates and the mayors.
They are, and the reason they're bipolar is because on one side will be the cathode, one side will be the anode.
Yes.
And the entire stack is in series, and so the plate on this side is the anode, and on this side it becomes the cathode. Exactly right. So you can see it here.
Yeah. So this is essentially what we saw before. So this one here, just a lineup of different cells, and now broken all down. And which one would be the bipolar plate?
Exactly. So we've zoomed in here, and obviously this is continuous in both directions.
Yes.
And if we look in the central element here, we've got this kind of gray piece, which is in this case, let's say metallic.
Yes.
In our instance, it's silicon. And you can see here that it's actually two pieces laminated together. And on one side, we have the air side with oxygen. On the other side, we have the hydrogen side. And in the middle, we'll have cooling channels, obviously, to keep the channel cool. And so, or the cell cool. And so actually that's what the bipolar plate does. So its principal job is to channel and distribute the reactants and products across the membrane and catalyst assembly so that we have a uniform, even distribution in the cell. No dry spots, no flooded spots, no hot spots or overly cool spots, just a nice uniform distribution. And because this membrane assembly is made up of lots of flexible parts, these bipolar plates create the structure that holds the cell shape.
Okay. So they are essentially, let's say, the two ends of the cell, if you want to say it that way.
They are, yeah, they definitely are.
So the anode for the one side, the cathode for the other.
Yeah.
And what you're doing now is, so we have, I guess a lot of the audience knows this as well. We've seen these made of metal, obviously, and we've seen them made of carbon materials.
Yes.
And now you are making them of silicon.
That's right.
Okay.
So traditionally, they were made of either stainless steel, or coated aluminium, coated titanium, or even graphite. A variety of different materials that all have kind of trade-off properties.
Yes.
Sometimes we're looking at the electrical conductive performance or the thermal conductive performance as well for removing heat from the system. Sometimes we're looking at durability or corrosion resistance. Sometimes it's lightness. Carbon is a lot lighter than the metal forms.
Okay. And so you brought one with you.
Right.
Here.
Well, and so the benefit of silicon actually is that it gives.
Could I just pick this up like this? Yeah.
Definitely, please do. It's silicon, but
so
it's
this
not that
is it's delicate, but not that delicate.
Yeah.
But it is entirely made of silicon.
This is a silicon crystal.
It's resting on this, so I don't know if you can just, for the sake of the video, just
sure. Yeah.
I know you're very peculiar about the fingerprints on this.
So silicon has a way of absorbing fingerprints that to remove them, you got to dip it back in acid. So we're not going to worry about that for this one. If we get fingerprints on it today, that's fine.
Okay, cool. So this is essentially the plate, and as far as I know, the plate. So you have these are already the the channels that we see here.
That's right.
In the photo.
That's right. So what we have, if you can imagine, this is built into a stack.
Yes.
And at each end of the stack, we'll have, a hydrogen inlet, an
Yes.
air inlet,
Yes.
water for cooling. So once those enter the stack at the manifold, they'll run down a variety of these different ports. Sometimes they're on two sides like this. We have designs where they're on four sides. And what we can see eventually is that, we'll flip it over for this one.
Yeah.
Those ports will have channels where it'll pass through the silicon plate.
Okay. Through to the other side.
And then it comes into the active area of the cell. So normally what would happen is the active area is separated from these by gaskets to prevent leakage and crossover.
Yeah. So there's a gasket running around. Yeah.
Exactly.
Yeah.
And so hydrogen is its own channel, air and oxygen in their own channel.
Yeah.
And obviously they'll react in the cell, but the gaskets prevent them from mixing.
So you would have this mare essentially just like resting on this side, and the bipolar plate is supplying essentially the media needed for the reaction. Right?
Yeah, exactly like that. And so on one side, let's say we would have it optimized for hydrogen distribution. If we were to flip it over and be the other side, as you show there, it'll be optimized for air and water removal.
Understood.
And this is actually a monopolar plate so that we could see inside the cell.
Yeah.
Normally, we would have cooling channels machined into this, or etched into this actually. And we would bond two plates together.
Okay. So just like we see here in the
exactly like you see there.
Okay.
Yeah.
Right. Okay. So now we see this is made of silicon, and we already touched it initially, and actually on this series we've also seen metal plates.
That's right.
And we've seen welding of metal plates and things. Now, honestly, silicon is kind of new. I mean, we've had fuel cell manufacturing companies for many years doing either metal or carbon. Why didn't anybody come up with silicon before?
So silicon itself as a material used in the semiconductor industry has gone through its own maturation process. So you can imagine fuel cells have been around, since the space race in the 60s and whatever. Whereas the silicon industry for semiconductors, especially ultra low cost. So obviously, people were inventing transistors on chips for CPUs, but those are very expensive silicon.
Yeah, okay.
The reason that silicon got so cheap so fast was essentially the development of the photovoltaic industry with solar cells.
Oh, right.
Everyone wanted cheap power. They wanted to print these cells.
Yeah.
And so actually let's say the original inventors of our technology and the founders of SILTRAX actually are some of the earliest silicon photovoltaics pioneers. They set up the first kind of gigawatt production lines.
Yeah.
And it was through 10 or 15 years of supply chain development that they were finally able to get to the point where silicon and the production lines were scalable enough and cheap enough, flexible enough to, let's say, move on from just PV cells and start making other products. And so about 5 years ago, we branched out from PV and we started to make fuel cell concepts.
So, I mean, just for the video, we actually brought some sand.
We brought some sand.
And the reason why was because this is, in researching this topic, I found it's amazing how silicon is in so many places.
Silicon's everywhere, right?
And even the glass is partly made of that. And so is it hard to come from sand, and I know this isn't the most pure form of it, to this? Like, what do you have to do to get from there?
So it is.
From here to there.
So it is. So first of all, that's silicon dioxide.
Okay.
So it's oxidized.
Oh, it's oxidized. Okay, you don't want that.
Well, we have to take, that is the actual raw material. It starts as pure sand.
Yeah.
And they'll grow crystals of pure silicon out of that, removing the oxide.
Yes.
And they'll create these giant ingots, actually. They can be a couple of meters long.
All right.
And the ingot is essentially a pure semiconductor grade silicon. And during the growth process of that crystal, we'll introduce chemical dopants.
Okay.
So that we
doping.
can,
Okay.
yeah, we have
Just
to,
like the solar ones as well. I think those ones are.
well, they are, yeah, they're doped
yeah.
silicon.
Okay.
And the dopants allow us to tune the properties of the plate.
Oh, right.
So that happens right at the beginning, at the creation of the material.
Right.
If we want a specific conductivity, thermal performance, or corrosion resistance, or a variety of other different parameters, we dope that silicon crystal so that all of those properties are built into the material.
Yeah.
It's not a coating or a process that's applied later. It's
Yeah.
built into the material. And then those silicon crystals are actually sawn into wafers,
Please. Oh, okay. Right.
into wafer blanks.
Mm-hmm.
And then the wafer blanks will be processed to, some mechanical, it could be machining to remove the size or create the kind of shape that we want. And then we'll etch ports all the way through, like in these examples, or we can etch different flow fields of different designs with incredible accuracy.
Okay. So also all these channels are etched in.
They're etched.
Yeah.
That's exactly
and when
right.
you etch, so is it like you have with the microchips a photo application as well? Or?
It is laser based. That's right.
Laser-based,
So
okay.
so they use a laser to create masks on the surface of the silicon, and those the areas that are masked can be removed using an alkaline process.
Okay. All right. Okay. Right.
And that's what we can achieve.
Ah, okay.
So we've got a cross section of a plate here, and the benefit of etching, because obviously you've talked about metallic and graphite that you've had on the program before, and those might use machining processes or stamping processes. This is a microscopy of the cross section of one of those plates, and we can tune these dimensions in any way that we want. We can make the overall plate thickness down to 100 or 200 microns. We can grow the plate thickness to, 800 or a millimeter if we'd like.
Right.
And then once we have the overall plate thickness, we can choose the kind of shape of the features. So we have these landings, and we have the flow channels ultimately that the material, hydrogen or air or water, will flow through.
Yeah. I see this is quite some precision. considering that these are very small dimensions, and this is very zoomed in here. So
it's probably actually excessive precision. It's probably too precise for the process. Most of it, this is perfect corners and shapes.
And so that is already, let's say, one of the differences in terms of material, right, to metal and to any other alternative, the ability to make these kind of smaller channels.
So we can now go into what we call microchannels.
Okay.
And so we can massively increase the surface area of the reaction space on the plate by tuning these down to the micron level if we wanted to, whereas you can't achieve that resolution in metallic plates or graphite plates.
So that is obviously advantageous.
It's the principal benefit. It's probably the principal. Aside from the material properties being fantastic in electrical conductivity and thermal conductivity and corrosion resistance, the reason that we're able to achieve incredible performance using a silicon plate is we can really tune pressure drop and reactant flow, and the management of bubble formation and clearance of byproducts, such that these plates now we've achieved sustain up to 5 amps per square centimeter using silicon plates. And most of that is by mitigating the mass transport limitations. So inside a cell, if you want to try and ramp up that current, you need to really push hydrogen and air in and remove that water. Otherwise, everything becomes a rate limiting step inside your cell. And because we've been able to design these flow fields with incredible accuracy and microchannels, we can sustain 4 or 5 amps per square centimeter without mass transport limitations.
Right. Okay, so I know this is maybe too basic, but so for metal, it's clear that conducts electricity. For silicon, I always have to think now? Because I understand it changed. It's a semiconductor, so not always a conductor.
But when it's doped,
Yeah,
we can push it towards almost conductor status.
okay.
Yeah, it's the doping.
It's the doping. So then it gets conductivity very similar to metal.
That's right. Yeah.
Wow.
Yeah.
Okay.
Oh, even more than metal. So yeah. So this is not going to outperform copper, for example. Copper is the copper standard.
Yeah.
But coated titanium, aluminium, stainless steel.
Yes.
This outperforms all of them in terms of conductivity.
Okay, so you dope silicon and you can like conduct better than metal. Thank you. I'm learning something here.
Yeah.
But then, whilst we're talking about, take us through. So we've talked about improved flow field that you could make.
Yeah.
What else would you say makes a difference? And I even I read somewhere you guys even broke a record with this now. And I said in the intro you want to change the industry. Give us 2-3 hints about that.
Okay.
What you want to do here.
There's a lot to unpack there, but let's run with the headline first.
Yes.
Because breaking the world record was really important to us. We knew when we started working with silicon that it was going to be transformative. We knew even just from the early designs that the potential there was going to far exceed. It was going to be a paradigm shift away from the existing technologies.
Yeah. Okay.
And so earlier this year, we called it the G100 stack. It was originally intended to be only 100 kilowatts, but it's now the version that we sent away for performance verification to Rhineland was rated at 150 kilowatts. And actually now that stack pushes 200 kilowatts or even more.
All right.
But same stack. But it was sent off for independent validation by TÜV.
Okay.
And we've achieved 9.7 kilowatts per liter, the volumetric density, and I think it's 9.4 kilowatts per kilogram gravimetric density, which is in both aspects record breaking.
Yeah. I mean, TÜV, obviously the German quality standards company that does a lot of certification and things like that. I think we've had 1 or 2 videos with them here as well, and so they've independently verified the fact that you can achieve such volumetric density and gravimetric density with your stack. So more than what we've seen in other areas.
They did a couple of things for us as well. It wasn't just that. I think one of the most important things was that it was a standardized and compliant cell as well. So we manufacture in China and we were using the GB standard, which are essentially an analog of what we use in Europe and in Australia as well, in terms of the fuel cell standard. But they wanted to show that it was a representative, a real world cell as well. So it wasn't a cherry picked, short stack. It was a 150 kilowatt stack that went for validation, and it used over 320 cells. And so in that design, you're going to have some good performing cells and bad performing cells, and it's the average of all of those cells together.
And you go to 9.7 kilowatts per
liter.
Okay. So I need to ask, you didn't go for 10?
Okay. So expect a press release soon.
Okay.
We've achieved 10.
All right.
And so the product, obviously, that was 6 months ago. The product is constantly evolving.
Okay. So you're even hoping to get more.
There's a lot more to unlock.
All right.
There's definitely a lot more to unlock.
Speaking of product, and everyone tends to ask, can I buy a stack made of silicon now?
You can. And so look, this is a tricky question because all of the customers that want to buy stacks from us and all have their own applications. So some of them are aircraft, some of them are drones, large aircraft, small aircraft. Drones, obviously, very lightweight. It could be vehicles, it could be stationary applications. What I'm trying to say is there are so many different customer requirements out there for us that we have created these kind of 3 standardized sizes. But you might want to buy these, but these are probably not the ones you'll end up buying because it's just as easy for us because we can etch any design into silicon.
All right.
If you just came to us and said, look, I saw the G100, it pulled 9.7 kilowatts per liter. I need a similar stack of a similar design. while we have the G100 in the catalog, we'll probably end up creating the right design and shape for your application.
Okay. So we could make it a 200 megawatts, kilowatts.
Yeah. So we
kilowatt stack. And I could come with my own design also.
Right. So let's start.
What is it that you guys then do? You design yourselves?
Let's start from the top. So we created these 3 sizes to showcase applications at different performance levels for different applications. But every time, and so we send these cells out, for example, as samples to customers. They can put them on the test bench. They can create prototypes using these samples. But ultimately, when they want to build a final product around a stack, one of the benefits of using us is that we can create a custom stack to fit exactly the size and shape of the location that you want in your application. And so we might start with a G5 stack that looks like this. Maybe it'll have fewer cells, maybe it's slightly longer, but maybe you want a longer side or a short side or a slightly different fit.
Make all that.
Or for some customers, they come to us with their own proprietary GDL MEA system. And they say, we need our port locations in a different spot on the plate, or we would like the flow pattern to be optimized in a slightly different way.
And then you'd manufacture it.
And all of that, because of the versatility of using the silicon PV process, essentially it's loading CAD files. And so we load CAD files into the silicon the plant, and it moves the port locations on the blanks to wherever you need them. It moves the flow fields to wherever you need them.
I find it amazing, especially these values that you've achieved here. I know that some nations even, set targets for these kind of things. I think like Japan has, and the US. Exactly. And you guys have, you're an early achievers on those targets, if I understand you correctly.
It feels pretty good. Yeah. A lot of those targets are even set for 2030, 2035 targets, 10 years from now. And the aim or the goal of those targets is to give, I guess, all, in the industry, there's so many different pieces of the puzzle, whether you're working on the stack or the MEA or even cooling or humidification, all these different things. And ultimately, we have to try and package those into specific applications. And so we give people common goals to work towards, and one of those is power density.
So and I know we're running short of time, but there are 2 more elephants in the room. So apart from all the, let's say, power density magic, what about the durability and the cost?
Okay, definitely.
Cost.
Okay.
If you say it's cheaper than anything else, I think that's the easiest way to sell it.
So if anyone's handled silicon before, when you have one of them out in the world like this, it can seem a little fragile. It's like having a thin piece of glass. But when they are it's still quite mechanically rigid, and it's quite mechanically strong. But when we assemble those into stacks and we have the mechanical compression across those, more than a megapascal of force over 300 or 400 cells, it essentially locks up like it was a silicon brick again. And so they are incredibly rigid, incredibly strong and robust. And so the fragility of silicon might only be during the assembly process and the handling process, but once it's in a stack, it's very robust.
And when I'm talking durability, I mean also the chemical aspect. So can it get eaten up?
So this is where silicon wins actually. So silicon is inert in acidic environments. Right. So we're not using these in alkaline cells, for example, where the alkaline will etch them, but in acidic environments where we have, free hydrogen ions, it is literally completely inert.
So will not work for alkaline stacks.
We might be able to create a coating for to work, but no. Silicon is processed in alkaline. And resistant to acid.
So that's in terms of durability. In terms of cost, I mean, you said your founders come from solar, and we saw solar, the price. Can we expect that as well? Lower cost?
So that's their intention. They've been watching the fuel cell industry, and they think one of the holdups for adoption, obviously, there's hydrogen price and these kind of things, but one of the holdups is that the fuel cell is just expensive. And so we're doing our part. Obviously, there's catalyst in there and there's membrane in there. But by leveraging, the photovoltaic scale of the process, we really can drive the price of these plates down. And ultimately, silicon as a raw material is not particularly expensive. And then once we start to manufacture at scale, the scale price is not very expensive.
Okay. But the today price is still, it's still in the evolving stage.
So right now, we've invested, let's say, millions of dollars to create a clean room environment with a pilot plant. And so if we're ordering one stack at a time, we're pricing them nominally. We want people to buy them off us and test them out in their applications. And so let's say we're not pricing them at their true cost right now. We just want to get stacks in people's hands.
Oh, good. Okay, perfect. So you mentioned the 10 is on the line. Can you give us one or two sentences of what's coming? So obviously you guys are, let me say, newer to the market. You have lots of experience on the photovoltaic industry. Obviously, this is exciting because everything that drives the cost down in the hydrogen sector is good. So what's the outlook?
Look, the outlook is extreme, actually. It's amazing. Since launching the media release, the statement about our performance, 6 months ago, the number of OEMs and integrators, whether it's aviation or automotive or marine, that have reached out to us to request stack samples, for their own independent validation, and then also to trial their own designs and MEAs. I don't even know what to say. The phone has been ringing off the hook. And we just hope that this platform will allow all of those integrators to achieve, the tipping point economics in their own applications.
In their own applications. Okay. So you don't want to, in their own applications, you don't want to be owner of the applications.
We're an unlocking technology. We're an enabling technology. We're not flying planes. We're not creating drones. We're creating plates for stacks. And all of those people will have their own economics, whether it's, the fuel efficiency or the overall cost of delivering their service, whether it's passengers flown or packages delivered. And if we can help them bring their business cases into fruition, then that's our job. And so, because ultimately we want to sell plates. We want to sell millions of plates. Millions of plates.
I think that's a good point to end. Millions. Thank you very much, Daniel, for coming over. This has been very interesting, how silicon is coming into the hydrogen industry. Thank you so much.
You're very welcome. Well, thank you so much for the platform.
And thank you for watching. If you are interested in more of this, we have a whole series of videos around hydrogen. If you can get in touch with people like Daniel, go on Hyfindr.com, where you can see these products, learn all about them.
That's right. We're showcased on Hyfindr.com. So find us, click through, and you'll get to talk to me.
Perfect. Thank you so much. Have a wonderful day.